Hello APC Mechanics students in Unit 1 Kinematics, Class 5 Freefall Motion Part 2. Let me recap and say what we have done in the previous lecture. We've studied a special case of a freefall motion in which an object is dropped from rest. We have introduced two shortcuts that are very crucial. The time lapse, which is the time required for an object to cover a vertical distance h, and the impact speed before it hits the ground in terms of h. Now, in today's lecture, we will study another particular case of free fall motion in which an object is launched upward with some initial velocity. Then an object is launched with an initial velocity upward. This is the initial launch, which coincides with the origin. It is a special case of a free fall problem simply because the only force acting on the object is the force of gravity, and we're gonna neglect a resistance. Near the surface of a planet, we know now that the acceleration is given by g, which is considered to be constant near the surface of the planet, and in particular if we're talking about Earth, it's given by 10 meters per second square. And here let me explain something very crucial. Now, explicitly in the equations of motion we don't have acceleration, however we have the component of the acceleration given by ax and ay. Now, why the component of the acceleration is different from the acceleration itself? Now, ay might be plus g, which is 10 meters per second square, and it might be minus g, that is minus 10 meters per second square, and this depends on the direction of the y-axis with respect to the acceleration. Here, because the motion is upward, it's easier to take the direction of the y-axis to be upward. Alright, so this it's a matter of choice. Let me repeat and say because the motion is upward, a better choice to choose the y direction to be upward, and in this case the acceleration would be in an opposite direction to the y-axis. For this reason, it is given by ay minus 10 meters per second square. However, in the previous case, because the motion was downward, we have chosen the y direction to be downward, and in that case, ay would be given by 10 meters per second square because the direction was downward, alright, of the y-axis. Now, starting from initial value, the speed decreases at a rate of 10 meters per second each second. Now, why the speed is decreasing? Here the motion is upward, so the velocity is up, acceleration is down. Velocity and acceleration have opposite direction, which means that the speed is decreasing. And as you see that, the speed will decrease at a rate of 10 meters per second. So each slice, we expect that for each slice of time, the speed will decrease by a value of 10 until it reaches the zero velocity. The covered distance decreases quadratically each second, 45, 35, 25, 15, and 5. We will demonstrate that the relation derived previously for a free fall with no initial velocity hold here, since the problem is completely reversible and we're making use of symmetry. And I will refer to that later. Now, section 1, time lapse for a maximum height. Now, here in this section, we are interested to calculate the time required for the object to reach the maximum height. So let me explain. We have an object launched upward, so we will choose the y direction to be up. The initial position coincides with the origin. This is the instant taken to be time is equal to 0. So we can wonder or ask ourselves, what is the time required to reach the maximum height? Okay, we will demonstrate that the time would be given also by 2h radical 2h over g, but it would be given a different interpretation. Now let's start. An object launched with an initial velocity upward is submitted to a constant acceleration due to gravity. So this is a specific type of motion, uniform varied motion. Then we can use any equation related to this motion, and in particular I'm gonna use this one. We're gonna swap x by y. The initial position is 0, so we have the following equation. Now, what we have done in the case of free fall dropped from rest, this term was 0 because the initial velocity is 0, but here we cannot neglect this term because we have an initial velocity. So this is the first equation that we're gonna play with. And I promise to prove for you that t, the time lapse to reach the maximum height, is given by 2h over g. And in order to do so, we need to make use of another equation which relates the final speed to the initial speed plus the acceleration or the linear term. Let's swap x by y. And here let me also say something very important. And the maximum height is defined by the constraint Vy is equal 0. Why so? Because if we throw an object up, it's gonna reach a maximum height, but at that maximum height, the object will start to change direction momentarily and drops down. So this is the point of change of direction, and we know that an object cannot change direction unless the velocity of this object momentarily changes. So the maximum height is given by the vanishing velocity along the y direction. Alright, so the maximum height is defined by the constraint Vy is equal to 0. Now replacing this here and solving for the initial velocity that we would like to replace it here, we would get that the initial velocity is given by minus ayt. So let's replace the second equation and the first one, and we would get minus ayt multiplied by t plus half ayt square, and that would be minus ayt square because t multiplied by t is t square plus half ayt square. Now here what do we have? We can factor out ayt square. We have minus 1 plus half, and minus 1 plus half, if we do the common denominator thing, that would be minus 2 over 2 plus half, that would be minus half. Then in this case the final term would be minus half ayt square. So the position is given by minus half ayt square. About which position we're talking? We're talking about the final position, which is given by h measured with respect to the origin. And remember that because the y-axis is up and the gravity or the acceleration is down, then ay is given by minus g, and this is a matter of choice. So h would be given by half gt square, or in other sense t would be given by radical 2h over g, which is the same expression that we have determined previously. So t up is the time lapse for an initial launch to reach maximum height, h would be the maximum height, and g is g. Now this in this case would be given a different interpretation, and we say as follows. This is the time required for the object to reach the maximum height, where in the case of an object dropped from rest, we would say it's the time required to cover a vertical distance h downward. Alright, now section 3, maximum height given initial velocity. In this section we are interested in relating the maximum height to the initial velocity. So we can say as follows. Suppose that we launch an object upward with an initial velocity. What would be the maximum height, how would be the maximum height related to the initial velocity? So it is uniform varied motion, and we're gonna use the following equation, which is the equation that relates the final velocity to the initial velocity with the displacement or the height. Let's swap x by y. Now, because we are talking about the maximum height, which is the point under which the object changes direction, and it's defined by vanishing velocity, and the initial position is considered or coincides with the origin, and let's replace the final position with the maximum height, and we know that in this case ay is given by minus gy because the y-axis is up, gravity is down. And we would have, if ay is minus g, here we would have an additional minus sign, and y is h, and if we solve for vy0 we would have radical 2gh. Now h, let's consider this one. H is equal to v square over 2g. Vy0 is the initial velocity, h is the maximum height, and g is g. So as you see that the equations are pretty the same that we have done previously, but the interpretation is different. How do we interpret this equation, these relations? If an object is given an initial velocity upward, then the maximum height reached by the object is given by h is v square over 2g. However, for this one, this is better to be interpreted if an object is dropped from rest. If the object is dropped from rest and it's gonna cover a vertical distance h, then the final speed would be given by radical 2gh. And here I'm talking about, or I'm referring to the previous case in which the object is dropped from rest. So as you can see that the formulas are pretty the same due to the symmetry of the problem if you think about it, but the interpretation is different. Now section 4. Okay, here I will just give a counter example about a free fall motion and just to clarify some points. Section 4, object launched downward with an initial velocity downward. So the case 1 that we have discussed is that an object is dropped from rest. Case 2, an object is launched upward with an initial velocity. And we've said that they have some common points. And in case 3, now what we're gonna do is that we will launch an object downward with an initial velocity. An object is launched with an initial velocity downward. Problems in kinematics might look similar, however, one should be very careful when generalizing equations from one scenario to another, and things might get pretty complicated. Here in this case, we cannot use the following relations. T is radical to h over g, v is radical to gh. Although it's a free fall problem, but it's neither case 1 or case 2, because we're giving the object initial velocity downward. It's not dropped from rest or launched upward. The way to approach the problem is to use kinematic equations from scratch. Pay attention to start by defining the origin and the oriented axis. For example, here in case 3, because the motion is downward, it's better to introduce the y-axis to be downward, as I have done here. Okay. One suggestion is to take the origin to be the initial position and the direction of the oriented axis to be along the direction of motion, which is downward. Okay, exercise 1. So as I always suggest, pause the video, try to solve it, think about it, then refer back to the solution. An object of unknown mass is initially at rest and dropped from a height h. It reaches the ground with a velocity v1. The same object is then raised again to the same height h, but this time is thrown downward with velocity v1. It now reaches the ground with a new velocity v2. How is v2 related to v1? So let me explain the problem here. So the first thing that we're gonna do is that this is the ground. Here we have an object. In the first case, initially at rest and dropped, so we're gonna leave the object to fall freely from rest. It will reach the ground with a velocity v1. Now what we're gonna do next is that the object is raised again to the same height, and in this case we will drop the object with a velocity v1, which is the same velocity v1 here, and it will gain a new speed or new velocity v2. We need to see how is v2 related to v1. Now first of all, we know that in the first part of the problem, v1 can be easily written as radical to gh. This is capital H, because this is a case of a free fall problem with no initial velocity. Now what about v2? We cannot say v2 is radical to gh, because simply we have an initial velocity downward. So we need to solve it by hand. We will choose the y-axis to be down, and in this case ay is given by plus g, because the acceleration has the same direction of y direction is down because the motion is down. So in this case we're gonna use the equation vy square is vy 0 square plus 2a, this should be plus 2ay delta y. Now delta y is the displacement, which is capital H, and the acceleration would be g. Now vy square is v2 square is equal to v1 square plus 2gh. Now v2 would be radical v1 square plus 2gh, but we know that v1 square is 2gh, so this 2gh can be replaced by v1 square. So we have v1 square plus v1 square, and that would be, let me continue here, radical of 2v1 square, and that would be radical to v1. So v2 is radical to v1, and the correct choice in this case is C. Okay, exercise 2. Ball 1 is dropped from rest. This is ball 1, v is equal to 0. From a tower of height h, as shown above, at the same instant ball 2 is launched upward from the ground with an initial velocity v0. If air resistance is negligible, at what time t will the two balls pass each other? So we are talking about the meeting event, and now we're more familiar with the meeting event. We need to set up the position time equation for each object. So in order to do so, we need to choose our oriented y-axis. You can choose it either down or up, because 1 is moving down and 2 is moving up. For me, it's easier to choose it to be down. And next we need to choose the origin. I will consider this to be the origin. And now we can set up the equation, the position time equation for each object. For 1, the initial position is the origin to be 0. There is no initial speed. Plus half, in this case the acceleration ay would be plus g, because the y-axis is chosen to be down along the direction of the acceleration. That would be gt square. So half gt square. What about y2? It is given an initial position in the positive direction to be h. It is given an initial velocity in the negative direction to be minus v0t and plus half gt square. Now we will say that y1 is equal to y2. This is the equation given by the meeting event. Half gt square is equal to h minus v0t plus half gt square. That would cancel with this. We are left with a linear equation in t. And if we solve for t is given by h over v0, and in this case the correct answer would be C. Then thank you for watching, and see you soon in a new one.